Welcome you all to this video on load flow analysis. This is unit 5 of the subject Power System 2. It is there for third year BTech, and I am Uttam Satpute, Professor in Electrical Engineering Department at Dr. D.Y. Patil Pratishthan's College of Engineering, Saurankanagar. So let us start with the syllabus. It is unit 5. It is load flow analysis. So in this unit 5, we shall be learning load flow problem and how this load flow can be done using these methods, that is Gauss-Seidel, Newton-Raphson, decoupled load flow, then fast decoupled load flow, and then we will have a comparison between these all load flow methods, and we are expecting some numerical treatments also. Now this unit 5, the 4 learning outcomes have been defined. Yellow 1, that is load flow problem. LO2, there is load flow by Gauss-Seidel, the level goes up to 4. Then we have learning outcome number 3, that is load flow by Newton-Raphson, the level goes up to 4. Then the last learning outcome, it is load flow by decoupled load flow and fast decoupled load flow, and we will have a comparison also. So only 4 learning outcomes are defined here. Now let us start with the first learning outcome, that is load flow problem. But before going to this problem directly, let us have some prerequisite. So just I am showing you some of the Maharashtra state. What is the generation capacity of Maharashtra state? So here in Maharashtra, this is the map shown here, and we have 4 type of generations: thermal, hydro, gas turbine, and solar energy. Now, total thermal power generation in Maharashtra state is 9,540 megawatt, and major generation is from Chandrapur, which is 2,920 megawatt. So, where is Chandrapur? Chandrapur is over here. You can see this is Chandrapur thermal power station, and in Chandrapur also we have solar power generation. We can see here Chandrapur solar power generation. It is 180 megawatt generation is there in Chandrapur, and there are other thermal stations. So we can identify it with this symbol. So here we have in Kordi and Kaparkeda, we have 2 thermal power stations. In Kordi, we have 2,190 megawatt, and in Kaparkeda, here it is 1,340 megawatt generation. So we have other thermal power stations, one here in Akola, one in Bhusawal, one in Parli here, and we have one in Tarapur, and then we have one here in Mumbai, which is Tata thermal power stations, and here also we have in Nashik, we have this one thermal power station. Similarly, we have Hydel power station. The total Hydel power station capacity in Maharashtra is 2,580 megawatt, and the major generation is from Koina Hydro, which is 1,956. So where is Koina power plant? The Koina power plant is over here. So this is here we have Hydel power station, and apart from that we have gas turbine. There are 2 units of gas turbine. So one unit we can identify here in uh, Dabihod, okay, and one here in Pench, yeah. Okay, so these are the installation capacity of Maharashtra state. Now, why I am showing this? Because we have to understand that our generations, they are not at one place; they are distributed. Okay, in the total Maharashtra. Now, how these generations are connected to one another so that they can supply power to the load. So we have a transmission network. So here this is shown the transmission network of Maharashtra state. It is so complicated to understand, but just I will identify some of the major lines here. So there is 100, there are lines of different voltage levels: 100 kV, 110 kV, 132 kV, 220 kV, 400 kV, and we have HVDC line also, and the highest transmission capacity voltage, it is 765 kV also line is there in Maharashtra. So now these colors you can identify these dark, this light green color. They show 100 kV single line, and this dark green color it shows 100 kV single line, and now so these are different transmission lines. So I will not can give you some some picture of uh, this, but we can understand it. So what is the point here? The transmission network. One transmission network, it connects all the generations, and the power is transferred from generation to load. Okay, so now let us come to our learning outcome number one, that is load flow problem. So what is load flow analysis? Study or problem, sometimes it's called as study or problem. So what is load flow analysis? Load flow analysis is also known as power flow analysis. It is to be understood. Load means from generation to load, we have a transmission lines. The generations, they are at different locations, and they are connected by transmission line to the loads. So from generation, from different generation, how power flow to the load, that is called as power flow analysis, or it is called as load flow analysis. Now to do this load flow analysis, we should have some equations, we should have some model, and that model, it is developed under steady state operating condition. What is steady state operating condition? Means the generation power, it is fixed, the load power is fixed, the transmission network is fixed. There is not change in any of these parameters with respect to time. They are fixed static. So it is called as steady state analysis also. It is called as computational procedure. That is what I told, that to do load flow analysis or power flow analysis, we require models. So, and those models we need to solve it. So it is altogether, it is computational procedure that determine the steady state operating condition of power system. Then, now why we have to do this load flow analysis? Basically, it is done for planning the transmission network or generation or load, whatever it is. And there is, if any, there is an additional line requirement and associated equipment, what should be the rating and all. So all that, for doing that planning, load flow study is done. Similarly, for the purpose of design, if I want to lay on one transmission line, so what should be its operating voltage? What should be its power capacity or line current capacity? So all that aspects we can design using this load flow analysis. Also, there is one more important point. We can know the operating state of the power system, whether the power system is operating under a normal state or abnormal state. So by performing load flow analysis, we can identify that. Then it is very, very important to understand one more point, that load flow study is the basic study required for carrying out other studies. Like if you're doing short circuit studies or transient stability study or economical dispatch or security analysis or reliability studies, for all of these studies we require first initially load flow study to be performed. Okay, so this is the same way we should write in the exam if they ask what is load flow analysis or study or problem. Okay, now what is the aim of load flow problem? So load flow, when we do load flow analysis, we come to know what is the voltage magnitude and phase angle at a particular point, particularly at the bus. Okay, then what is the reactive and reactive power at the bus and in the transmission line. At various points of the power system, we can identify what is the real power and what is the reactive power. Also, we can find the real and reactive power loss in the transmission line. So here it is graphically shown. This is a computational model, load flow, and what are the inputs required to this computation? So we require the bus data. So we will come to know later on what is bus data actually. Line data means how many lines are there, what are their admittance, and all related to that. Then generation. What is the generation power, real power, reactive power, and what is the load data. What load, how much load demands the power, real and reactive power. Then after computation, we get the voltage magnitude, voltage angle at the bus or any other point in the system, then real and reactive power at the bus in the transmission line, current flow in the transmission line, and power losses. So computation of all these parameters is called as load flow analysis. Okay, so just as an out of interest, I'm showing you uh, some uh, some of the examples here. Now consider that we have a load here which is 400 megawatt 250 MVR. This is my load requirement. So this is my Kolhapur city, and my Kolhapur city is required this much power. 400 megawatt 250 MVR is my requirement. Now where do I get this power? So I have two generations. So here I have generation, say 2. This is my generation number 2, and this is my generation number 1. Okay, now I have three buses here. So this bus number 1, now here this is called as slack bus. Later on we will try to understand what is slack bus, but for the time being just understand the slack bus. And here the voltage is fixed. Now they have given the data that already in the previous diagram I told that the input data required. Now the input data here, it is the voltage at this bus, it is 1.05 and angle 0. This is given. And nothing is given about this generation. What is generation? I don't know. So it is written as 0 megawatt and 0 MVR. I don't know what power it is being generated from this. Okay, and this is my initial inputs. Now generation 2, the power is given that 200 megawatt power can be given. It is at the most. Okay, not less than that or more than that. It is fixed 200 megawatt it will give you. And there is not any data regarding the reactive power that can be given. But voltage at this bus, it is fixed 1.04 per unit. Okay. Now here there is another, here the voltage is also uh, no, here there is not voltage is fixed, but here this is an assumption. Later on when we go to load flow problem, you'll understand. But now you just understand that now this is my requirement. My city Kolhapur, the load is 400 megawatt 250 MVR, and I have two generations, and these are the transmission network. So now I want to find out what should be the generation from the buses, from the plants, and what will be the power flow in the transmission line and all that parameter. Now this simulation is done in one of the power simulation software. Just I will show you the result. Now this is the result obtained after load flow. Now you can see here that we have a requirement of 400 megawatt at the load, and this is met by this. So 170 megawatt power, it is coming from this plant. So now there is a loss when this power flow in the transmission line. There is a power loss of 1.39 megawatt, and uh, okay, so the total now, the other rest of the power, it goes from here in this way. So the total generation is 218 megawatt. Out of 218 megawatt, 179 it flows this line, and 39 megawatt flows in this line. That comes to this. And from here, 200 megawatt generation is given. So 200 plus 38, 238 megawatt power. So you can see a 238 megawatt power, it flows through this, and then 229 plus 170, it will meet your requirement of 400 megawatt. So this data, what will be the generation, and even what will be the generation, what will be the power flow in the transmission line, and what will be the voltage, that also we will get after performing a load flow. Okay. Now, here there is one important point to be noted. What is that? We have seen here the red color. The red color is 112%. What it indicates that under this condition under this operating condition, this line this line it is overloaded 112%, means 12% it is loaded more than its capacity. So when if it is operated 12% more than its capacity, then obviously it will be interrupted. There will be some damage that may cause damage to this line. So we should take care of it. Now this line here we can see orange. It is 82% operating, means it is an orange alert that there is a possibility that this line may be overloaded if you don't take care of it. Now this line it is in the safe region, 70% it is overloaded its capacity, so there is not issue with this line. Now in the next paragraph, let us assume that due to some reasoning, this line is gone off. Then how this 400 megawatt power is met? So 400 megawatt power is met. So here you can see 400 megawatt entire power uh, it comes this way. So we can see here from here 200 megawatt, it goes to this 200 megawatt here, and this 200 megawatt is added with 270 megawatt, so this power flows in this way. But if the power flow happened in this way, then this line is overloading. It is more than its 190 129% overloading, more than its capacity. So obviously it is going to be interrupted, and this is showing that it is orange alert, that it is showing that this line is also going to be it is going to be uh, it is going to be also overloaded if this care is not taken. Now let us see another scenario. Now suppose if this line is gone off, and under this condition of load, if you perform load flow, then we can see here this line, it is going to be overloaded with 106% capacity. So we need to take care of it. Similarly, if you look at sorry, okay, okay. Now if this line is gone off due to some reasoning, then this line, the top line, it will be operated at 92% its capacity, and this is again overloaded by 5% capacity. So I am giving these different scenarios of operating. It is because only after performing load flow, we will come to know what will be the voltage level at the buses, what will be the power flow in the transmission lines, whether any of the line will be overloaded, and if it is overloaded, then what action we have to take it, and if there is any compensation is required. Now here we can see here. Now with the present load condition, we are giving some compensation of 223 MVR. This is from any sum of the fact device, and if you provide this compensation, it is you can take it from your static var compensator or something like that. Under this condition, you can see the scenario. Now none of the line is overloaded. This line is operating at 91% capacity. This is operating at 68 safer zone. This is operating at 60% capacity. So everything comes into the normal condition if we provide some compensation at the load side. So whatever reactive power requirement is there of the load, now it is made locally. So there is no reactive power taken from any of the generation, and that will cause your voltage profile to be improved, and your line flow will also be within the limits. So this is the point you should understand. Load flow study is very, very important study in the power system. Okay, so it will give you the voltage magnitude, what power flows in the line, losses also will come to know. Now you can see here, this here, here, just give you one. in this transmission line there is a real power loss of 5.7 megawatt and the reactive power loss is 11.57 MVAR. So you will come to know how much loss is there and what compensations are required and all that. Okay, so in this video, I will end up this video here. Thank you very much. We'll continue in the next video.